All right, everybody, we're back, and now we're going to talk about, I don't know, some statistics, or at least some pretty charts and distributions and all that fun stuff. So anyway, let's get rolling. This is going to be a quick one. Your book does a really good job of covering this material, and of course, you've kind of been through all of this on Khan Academy by now, I assume, as well. So we'll just get rolling. All right, histograms, distributions. Essentially, the message that I want you to take home from this is that it's a way to present your data. It's a way to start understanding your data and getting a feel for it. Because when you're just looking at thousands and thousands of numbers, it doesn't do you any good. You can't see what's there, right? At least for the average person, they don't. So what you need to do is you actually need to plot this in some way. And the most simple way to plot it is using a histogram, okay, and looking at the distribution of how that data is distributed across your sample. Historically, we typically like to break things up into ranges or bins, okay, also called a class interval, all sorts of different names for this stuff. So ultimately 10 or 20 ranges for your data set. Imagine age groups, right? When you're doing demographic stuff and you're looking at ages. If you broke that up into one column for every single age, it would get huge, right? The graph would be gigantic. You wouldn't be able to see what's going on. And it would just be too big to interpret. So we tend to break things down into smaller chunks, and like I said, 10 or 20 ranges is ideal. But the real purpose of this is is to get that visual analysis of what your distribution is. So all of your scores, how are they distributed across all the particular options? And what we're going to do is on the x-axis, we're going to put those different options, so to speak. So let's say we have a Likert type scale with 7 items, or 7 options like agree, disagree, strongly disagree, that type of stuff. We would put those across the bottom and then on the x-axis, and then we would do a physical count, the number of people scoring at 7 or at 5 or at 3, that type of thing. And you would plug people in and you would actually see a distribution of how those scores are distributed across your data set. You can only do this with ordinal, interval, and ratio level data. You can't really, you can kind of do it with nominal data, but it's really, there's almost no point. Usually with nominal data, you just throw it into a table and say, oh, here's how many people did this, here's how many people did that. Part of the reason there is that it doesn't connect. Nominal data doesn't connect each day, each point. But in ordinal and interval and ratio data, there is some sort of relationship between each point. One is, there's that order, and that order means something. So putting things in left to right or right to left, you're getting larger in some scale or smaller in some scale, that type of thing. So that's why it has some sort of meaning. You can see how skewed your data looks, and we'll look at a chart here in a minute that shows you that skew. All right, and that allows you specifically to decide what statistic you can use. When you start seeing skewed data, you automatically know that you're not going to be doing parametric statistics. And parametric statistics are ones that you use on normal distributions. And interestingly enough, a vast majority of the statistics you're going to run into in the field are parametric statistics. And the problem is that most of our data is not parametric, so we have to reconcile that issue. And the first step in reconciling that is making sure that you actually look at your data and find out if it's normally distributed or not. And then you can make some decisions from there. And as I've talked about before, that's one of my pet peeves, is using the wrong statistic with the wrong, with the wrong data set or the wrong distribution. Right? So here's a kind of a cheesy little one to look at. This is symmetrical, but not normal. Right? It would probably pass for normal in terms of if you were to run a test to find out if it was normal, but it depends on how many sample or what the n size is here and all that stuff. And anyway, you get the idea. Average drinks per week and ages. If this was a real histogram, if I wasn't using Excel to do this, if I was using something proper like SPSS, these bars wouldn't be separated from each other. They would be connected. Okay, so they would be mashed up against each other. So we've got average drinks per week, 5 to 10, 11 to 15, and 16 to 20. Now you can imagine if we had 40 different vertical lines there to represent 1 year of age for each person, each year of age from 5 up to 40, I guess it would be 35. So from 5 up to 40, we could have that many lines, but it would just be really mashed together. It would just look bad. And of course, there's going to be some 5-year-olds that don't drink at all, or maybe 5-year-olds didn't drink at all, but that type of thing. So you would end up with a lot of weird-looking data in there. So we tend to do it like this, just to get a picture of the data, and then you can, at this point, decide if the data is normally distributed, or you can at least come close to making that decision. Right? Now let's tweak this a little bit, and now we've got a skewed distribution. Right? As you can see, there's just a little bit down there on the 5 to 10, and it's actually a negative skew. All right, so the skewer, if you will, is pointing to the left, which is negative. Right? And again, at this point, we would know we're not normally distributed, and we would automatically put ourselves into non-parametric statistics. Okay? And again, the problems here are that the numbers aren't matched up, or the columns aren't matched up against each other. So it's not a real histogram, but basically it represents one. So. All right, line graphs, probably the most common thing out there that you're going to run into, at least in my world with doing the behavioral stuff and looking at the behavioral charts. It's easier to see things like rate and frequency and things like that when you start putting them in a line. And you can also start to see how those rates change and relate to each other. And it's very clean. It's simple to read, and a lot easier to read than a whole bunch of bar charts slapped on top of each other. The issue with a line graph, though, is that things need to be truly connected. And notice on here I have interval and ratio data. That's because ordinal data, you don't have that absolute understanding of the difference between each point, right? So you don't know if a 5 and a 7 is the same distance apart as a 3 and a 5 is with ordinal level data. But you do know that with interval and ratio. So the line, the fact that it's connecting those dots actually means something. And what you'll often see in the behavioral literature is that you'll get a baseline and a break, and you'll put a vertical condition in there. I think your book covers a little bit of that, and then it puts a line in there that breaks apart the baseline to the intervention phases or the multiple intervention phases, whatever it may be. And you do not draw across that. You don't connect your lines from conditions because it's a new condition. The behavior should be reacting differently. Right? So that's what's going on there. Let's see, what else do we have? All right. Interestingly enough, especially in the behavioral literature, a lot of times we're only going to present some of the data. And that seems a little bit odd, but sometimes you have to read these graphs cautiously, because with some line graphs and with some studies, they may or may not present everything that's there. Okay? They'll present just a little bit of the data to give you an idea of what's happened. In fact, I'm working on a study right now where we're doing that, and we've got 40 individual lines. Right? We have all these lines for all these students. It represents number of test attempts that they made throughout the quarter. And if I put all 40 of those lines on a graph, it's brutal, right? So you can't interpret anything. It just looks like a bunch of ink, just kind of ugly. So what I'm doing is I'm pulling out, it's 5 people that represent all the other ones. So, okay, find somebody that did it in this way, find, that took a bunch of attempts, find somebody that took the least number of attempts, and find a bunch of people in the middle, right? And we'll put all 5 of those lines on one graph, and then you can see kind of how those patterns existed. And there's a couple other things I'm doing with regard to that, making sure that every pattern that has been observed in the data is represented, but that's the basic procedure for it. We do that for a couple of reasons. Number one, space and clarity. And we tend to present ranges, though, as well. So I say, okay, here's the range for everybody. That allows you as the reader to interpret better what's going on. We say that at data point 1, here's this average individual, but scores did range from X to Z, right? And you can make that specific that way. It allows you guys to interpret better what's going on and just reiterate the fact that nothing's being hidden from you. Okay. The graph itself, a couple of quick rules. 3D is for Hollywood. Don't bother with it on your graphs. It's pointless. All right. If you're having to create graphs and charts for clients or for work or anything like that, you really should make them kind of like you saw in this presentation. I'm using the examples on purpose. And that's because the 3D graph is just for... Excel does it all the time, but it's just ugly, first off. And second off, you do use that third dimension for a reason. It's called the z-axis. And if you have a third dimension to represent, then you can do it. Otherwise, it's pointless. Right? It's just fluff, and we don't like fluff. Right? The abscissa and the ordinate x and y-axis are of equal lengths. Right? if at all possible. Sometimes that's not feasible, and I get it, but generally speaking, we like our graphs to be squares. Right? Make sure the scales are clean, and make sure the labels are clean. All right, let's look at some examples of this. Okay? So here's why you need everything to be clear, right? Because it's really easy to lie with graphs. Now, what you're about to see is all the same, the exact same data. Take a look at those. Nothing has changed. It's the exact same data. All I did was stretch out that graph. And notice that with that second graph, even though the data is the same, let's focus on the green line because that's kind of the most obvious one there. Notice that the reduction on the green line in the second graph doesn't look as good as it does, as big as it does in the first graph. But it is. It's exactly the same. So if I want to minimize the amount of change that I'm showing in my data, then I stretch my graph out. If I want to maximize it, I can stretch it vertically, right? And then it would really show a big drop for that green line. So we tend to like these things to be of equal length so you can get an accurate representation of what's going on with the data. Notice the other thing going on here is that I have fairly clear the scales, right? 0, 5, 10, 15. It's not confusing. Okay, I think I was talking there about the scales. So on the scales, what you notice on this one, 0, 5, 10, 15, it's pretty clear, not bad. I suppose I probably could have done it by 2s and then stopped at 14 because there's no data point that's up above an 11 there is what it looks like to me. So that's a little bit of some rules of thumb. Now, let's also notice a couple things about the labels here. Everything's labeled pretty well. Glue sniffing behavior in general. Total instances, I should probably say total instances of what, like what it is. And then the days that we recorded it on. So let's look at something different with just by changing one of those labels. Let's look and see what happens. Okay. Glue sniffing behavior total instances. Glue sniffing behavior total instances per minute. Notice we did 3, 5, 7, 9, 11. Notice I changed my scaling a little bit there. I didn't drop that down to 0. So there's a couple problems here. Let's go through the first one, that I changed the total instances to total instances per minute. So you see a dramatic change in what's being presented on the graph. And you should, in your head, be thinking about that, oh my gosh, that those kids were sniffing 11, 11 sniffs of glue a minute on the first day, and then they drop down and so on and so forth. The other problem that you see here is that the scale doesn't drop to 0. And when that scale doesn't drop to 0, you think that the behavior's gone to 0, right? So if we think of, it doesn't matter which one you're looking at now, but it drops to, say, 4, right? But when you first look at the graph, on the 4th day, it drops to 4 total instances of glue sniffing or sniffing per minute, but it looks like 0, right? It looks like it's darn near 0 because it's at the bottom of that graph. So you always want to include that 0 point in there as well. Theoretically, with the proper software, you're supposed to put that 0 point slightly above the x-axis, but with Excel, I can't do that very easily, so I didn't bother with this. But the point is that just by tweaking with your graphs a little bit, and tweaking with the scales, and tweaking with the titles, you can completely change the meaning and can change the interpretation of your graph. So a lot of people will lie with their graphs just to try and make a point, but if you actually look in there in more detail, you'll see that, oh, all right, well, this behavior didn't completely go away. These kids are still sniffing. At the end of the intervention, these kids are still sniffing glue at 4 or 5 times per minute, or whatever you want to say. So it's not that nice of a reduction, even though it looks like a really nice reduction. All right, that's about it for graphs. There's more in your book, and there's more on the Khan Academy. Take care.